the next talk will be presented by Piyush Khandelwal, who is co-authoring a paper on planning in action language BC while learning with costs.
Hey everyone, I hope you can hear me. My name is Piyush Khandelwal. This is joint work with Fangkai, Matteo, Leonetti, Vladimir, Lifschitz, and Peter Stone at the University of Texas at Austin. And I'll first motivate what we're trying to do. About a year ago, we moved into a new computer science building. At the same time, we just completed construction on these Segway-based robots. We've got 5 of them in our lab right now. So at that time, we wanted to figure out, hey, how can we actually get our robots to move around inside the building and do a lot of intelligent tasks autonomously, like deliver coffee, because that's really important to computer scientists, deliver objects from one place to another, and so on. So we wanted to come up with a domain-independent planning system to do this. Now, since I'm at ICAPS, I know a lot of you work with PDDL, and that's a pretty standard way of doing things here. But at UT, we've also got the group of Vladimir Lifschitz and one of his students, Fangkai, just completed work on a new action language called Action Language BC. So we use that, and what this paper is going to be about is how we can go about using Action Language BC for domain-independent planning on robots. So just to give you an overview of the system, this is very reminiscent of any standard planning system that you'd have. We have an action description in Action Language BC. This action description is translated to answer set programming description, which is then solved by an answer set solver. And we use an answer set solver called Klinger and use it to solve the planning problem. What we have is we execute the plan. We have execution monitoring to figure out situations where things are not going correctly. And we also do a bit of cost learning that I'll get to at the end of this talk. So I've been talking a bit about this Action Language BC. I'll give a brief description of it. Action Language BC is represented by a bunch of static laws and dynamic laws. So the static laws, the one on the top, they roughly correspond to PDDL axioms. And the dynamic laws are actions and action effects. So we also have a bunch of abbreviations that you can use directly in Action Language BC. There is a causes abbreviation which defines actions. You can specify default values. So as long as any fluent is consistent in your observations, you can use that as default value. You can also define inertial fluence. And you can also define preconditions by making certain actions under certain conditions non-executable. So the purpose of this work was to figure out if you could effectively use Action Language BC to do these sorts of planning tasks that we were interested in. And also some more things that came out of this work were, can we incorporate the true costs of actions? Can we learn these costs on the fly? And can we generate a plan despite missing information? And then acquire this information as part of the plan. All right, so I've just gone through the introduction for this talk. I'm going to next cover a bit more details about BC, a few details about the representation and the efficiency of solving a description in BC. Next, I'll talk about how we actually went about formalizing a mail collection task, and then we conducted some experiments on it. And I'll conclude with some remarks on future work. All right, so Action Language BC has some nice properties that we like. It can easily formulate both recursive and indirect action effects. And I'll give an example of a recursive action effect in a second. It can also formulate inertia. It's also a fully declarative language, and it's got very well-defined semantics under the stable model semantics. So what this means is that when you write a description in Action Language BC, it translates into a logic program, and it also translates into one single transition system. And using the underlying mathematical foundations, you can generate provably correct plans. All the plans generated through Action Language BC are provably correct. All right, so to give you an idea about why we like the fact that it could easily describe recursive action effects, I'll give you a small example. So one of the examples that we used in this work is that of a mail collection robot. The robot goes around the building, wants to collect mail that's intended for delivery from every person inside the building. Now what happens in this situation is like it needs to collect mail from these 4 people, but however, Dan decides to leave early, so Dan tells the robot, hey, I'm going to give my mail to Bob, so you should collect it from him. And that's all well and good, easily solvable, except after Dan leaves, Bob also decides to take home early and says that I'm going to give all the mail I have to Carol, and you should collect it from Carol. So what this means is that if the robot wants to collect the mail for all the 4 people, it only needs to visit Alice and Carol now. And it needs to understand that by visiting Carol, it's going to collect mail from both Bob and Dan, and that's where the recursive action effect comes in. Basically, because mail can be passed around recursively, when the robot actually collects mail from Carol, it needs to recursively understand that mail has been collected from both Bob and Dan as well. So to give you an idea and give you an idea of the representation inside Action Language BC, this is actually very, very simple to represent. So if you look in the top left corner here, in Action Language BC, you simply define that once you collect mail from a person, that person's mail is collected. And if somebody, then you can also define a static law which says that if you collect someone's mail, and if somebody else has passed their mail to them, then their mail is also collected. So that's just a 2-line description over there. We asked on the fast downward mailing list for PDDL solutions because none of us were PDDL experts, and these solutions were provided to us by Patrick Haslam. These were really ingenious solutions in PDDL to come up with the same problem. So if you have axioms inside PDDL, it's pretty simple. You similarly to Action Language BC, you define the transitive closure of passing mail around, and then you define a single action that collects mail, and you can collect mail from everyone. If you don't have axioms inside PDDL, it's still possible to do this using auxiliary actions, where you have an auxiliary action that computes this transitive closure of passing mail around, and then you collect mail from everyone. So the point is that this is still representable in both PDDL and Action Language BC. What we believe is the representation is slightly nicer in BC. Next note is about efficiency. So we tested satisfiability using an ASP description from the 4 easiest problems in the barman domain from the planning competition. Now this is where the engineer in me is a bit sad, but when we ran fast downward with the Llama 2011 configuration, and if you want to just get satisfiability for these 4 domains, you get a solution in seconds. If you're using an ASP description and the Klingo solver that we've used in our work, it takes about 15 to 20 minutes to solve this problem. Now, this basically means that the sort of problems that we are trying to solve inside the building were very, very simple in comparison. So for those kinds of problems, this solution works fine. But like a lot of work that's been presented, ICAPS has been trying to improve planning efficiency. Unfortunately, at this time, the system will not work for those kinds of problems. All right, so next I'm going to move on to how we actually went about formulating our robotics domains inside using Action Language BC, and how we did our work on our experiments. So for the first thing we did was we constructed a semantic map for our domain. So this is a 2D map of the domain that we used in simulation. You basically label all the locations, like over here, there's lab. You can also label all the doors. And then you specify approach points to each of these 2 doors. And that gives you a translation from how to approach a door using this semantic map. So for instance, this is what our simulator looks like. If you want to define the approach action using the approach points to a door, you can have low-level navigation controllers that can execute these actions. So for instance, approach door causes you to face that door. You can't approach a door if you're not in the same room as the door, and you can't approach it if you're already facing it. That's pretty trivial. Similarly, we can go about defining other actions, such as open door, go through a door, collect mail from a person. There are also a bunch of fluents inside this domain. such as like this room has this door and where the robot is, whether it's facing a door and so on. So once you put all of this together and you implement it on a real robot, this is what it looks like. Credits for this video go to, that was a bit loud. I'm going to disconnect. All right, so I'm going to disconnect the audio. So this is the implementation on the actual robot. For those of you close to the front half of the room, you can hear my laptop speaking this out loud. That's Shuchi opening the door for the robot, and it navigates inside the room. It's collecting mail from the first person over here, and once that's complete, it'll go about collecting mail from other people inside the room. So this is mail collection from the first person. We couldn't actually detect when we place something on it, so there's just a timer on the action right now. So once that's complete, the robot starts executing the next part of the plan, approaching a door, going through it, and then approaching the next location from where it's supposed to collect mail. So I should mention that these passing relations of how mail has been passed from one person to the next has already been implemented, has already been provided to the robot beforehand, and the robot just plans and executes this task. But anyway, that's good enough to give you an example of the implementation. I'll move back to the talk. So that's basically it. That's how we finally got a robot to collect mail from people inside the building. The next part I'm going to talk about is one of the other nice properties that came out of this is that if you're missing some information, can we acquire it on the fly? So assuming like we want to collect mail from Dan, we don't know where Dan is, but we know that Carol is aware about Dan's location. So we can introduce a new action, which is ask person location. And what that returns is that person's location to us. Now, the way the solver solves this plan is that at planning time, you don't actually know what fluent is going to be returned when we execute this action. So what it does is that it still generates the shortest plan using don't care non-determinism. So for instance, when we execute, it generates the plan. It says greet Carol, ask person location Dan, and then collect mail from Dan, because the shortest plan generation is equivalent to Dan being in the same room so that you don't have to go anywhere. So that's where the solver uses don't care non-determinism to solve this problem. When you actually execute this plan and get Dan's correct location, what happens is that execution monitoring says, hey, something's wrong, this is not what we expected, and we trigger replanning as before. All right, so this is basically what it looks like inside simulation. There's this robot going to Carol's office. It goes over there. In simulation, we can open doors automatically, which is sort of nice. It greets Carol and asks for Dan's location. We had a screen on our, we had like a terminal window for this, and we typed in the actual location, and then the robot replans and then goes to the new location where it's supposed to. All right, so since one of the other things we also wanted to care about were action costs and how we could learn these costs, action costs were easy. Clinger directly supports cost-based optimization as well. What we did was to introduce learning. We start with where all the costs initialized to 1 and use an exponentially weighted average to improve the cost of each action as time progresses. So every episode, the planner produces a plan with the current cost estimates, gets some samples, update all the cost estimates, and then goes to the next episode. The reason we were interested in learning these costs were that while we had distance metrics for all the navigation tasks, some of the passages are narrow, some of them are more crowded, and so on. So for a low-level navigation control, it can take varying amounts of time, somewhat independent of distance. So we did all our experiments on both in simulation and in the real world. So the simulation domain contains about 20 rooms and 25 doors. This is what the learning curve for the domain looks like. So what we have are the 6 best plans inside the domain. There are obviously a number of other correct plans which are not shown here. We provided the solver with 1 minute of planning time across 6 parallel threads. And we only search for plans up to 35 steps in length. And basically in about 25 episodes or so, it converges to the true lowest cost plan, which is over here. Similarly, we did experiments in the real robot domain as well, as you just saw. It's basically a much smaller domain. And this time, we don't even need to cut off planning after 1 minute of time. Optimal planning takes about 10 to 15 seconds. And we can converge a lot faster because this is a smaller domain. All right, I'm going to quickly conclude. So basically, the purpose of this work was to demonstrate that action language BC could be used for solving robotics tasks, such as the mail collection problem. True action costs can also be incorporated into planning using action language BC, and we also demonstrated a bit of learning. So this work is applicable to a number of robotics domains. Some of the nicer properties of action language BC are the fact that it's easier to represent indirect and recursively defined action effects. So that's where this is useful. And future work, again, going back to the problem that the efficiency of the system is not up to the mark right now. So we're looking at scalability right now and looking at how we can hierarchically decompose the domain and make the solutions come up faster. And I think that's it. So thank you.
This is nice work. So there's work that's very similar, at least the application, from Manuela Veloso's group. They've done work on cobots.
Yeah.
And it's basically the same environment. They have a robot going around
Right, yeah.
in an office environment. Now, I'm wondering if you have looked at that work.
Yes.
And if so, if you can comment on how your system compares. So for example, since you say BC is the contribution, right? So what are the advantages of using your approach versus what they do? So that's one. And then my other question is sort of related because they also end up having to do a lot of replanning. In fact, all of these applications, you end up having to constantly replan because you have to make assumptions. So given that your system seems to take quite a large amount of time, even just 1 minute is a long time.
Yeah, you're absolutely right.
So I was wondering if you could comment on that as well.
Sure. The first, I'm familiar with cobot. I haven't looked up into papers recently. So as to that, I wasn't aware if they were doing any domain-independent planning. So that's basically what the purpose of this work was, to have domain-independent planning using action language BC. The other thing is that action language BC, because it's based on top of answer set programming, it's a non-monotonic logic system, which has some nicer properties, but then again, like obviously, because of those nicer properties and slower solvers, the solution time is pretty long. As to the solution...
Sorry, can you give me an example of one of those? I'm just trying to figure out...
Oh, right. So, for instance, when you represent an answer set programming program, it's not just... you've got the concept of both of a hard negation and a soft negation. So, for instance, there is like, I know this person is in this room. I know this person is not in this room. And I can also say that, hey, I'm going to keep on assuming this person is going to stay in this room until I see any evidence of the fact that this person is not in this room. So that's the negation by failure component, which is a nice property to have. As to the planning time, we've actually already done some preliminary work into using hierarchical abstractions for planning time, and that actually works extremely well, specifically in domains like this, because if navigation is a major component of your domain, it's very easy to break it up hierarchically. So that works extremely well. We're still looking into some of the theoretical aspects because the underlying mathematical foundations for action language BC are very nice. And the problem is that if you break it up hierarchically, you lose a lot of those properties. And if you don't actually have those properties, then, and it's a slower system, it doesn't make sense to use it anymore. So we need to make sure that we have a better idea or better understanding of these properties as well.
You consider that this robotics domain provide a good illustration for the need of the form of non-monotonic reasoning and ramification techniques that BC buys you?
I believe so. So the mail collection task that's in this work was definitely a bit contrived because that was the first thing that we tried out. We wanted to construct a domain where we knew it had these nice properties. Some of the work we've done since then has started demonstrating that, like, tiny things come up where we realize that these recursive properties and so on are very, very nice to have. For instance, like if this room is like 3 separate locations, but my low-level planner can go to any object inside these 3 locations, it's nice to understand that these are all connected to one another recursively so that I can approach an object in any of these 3 locations.
Other questions? Well, thank you again.
Thank you.